Homework 4.2, Logarithmic Functions, Video 5, Some Properties of Logarithms. In the previous video, we evaluated 10 logarithms, really without a calculator. But some of the logarithms that we evaluated were easy because of certain structural features of the problem. For example, one of the problems that was easy to evaluate was the natural log of e, which is the same as log base e of e. Now, why was that one easy to evaluate? It was easy to evaluate because the base matched the argument. And so the power that turns the base into the argument was just 1. That will be true anytime the base and the argument match. So for any allowable base, remember the base has to be positive but not 1. For any allowable base, log base b of b is equal to 1. What about the second one, log base b of 1? Well, we had a problem previously that said log base 6 of 1. And do you remember why it was easy? Because we had an exponent rule that said anything to the 0 power is 1. So the fact that the base was 6 was actually irrelevant. What was relevant was that the base was 1. So as its own logarithm, the question this is asking is what power turns this base into 1? Well, 0 as a power will turn any base into 1. So we could say a property of logarithms is log base b of 1 is equal to 0. And I try to write my 1s when we're dealing with logarithms with the little hat and the base. The little like this instead of like that, because we're writing the letter L over and over. I want these to look different. Sometimes I catch it, sometimes I miss it. We saw a couple like this, and I'm not going to bring up the examples from the previous video because I'm just going to ask you the question that this is asking. The question this is asking is what power do I put on the base to make it look like that? What power would I put on b to make it look like b to the nth power? How about an nth power? This one was the tricky one. B to the log base b of n. I believe the one we had last time was 7 to the log base 7 of 5. But remember what I said about this one. I really didn't care what the log equaled. I only cared what the log did. In other words, I didn't care what this answer was. I cared what this answer did. So same thing back over here. I don't know what log base b of n equals, but I know what its answer does. The answer to this log is the power that turns b into n. So the thing under my hand is a power that turns b into n. Well, the thing under my hand is a power that's on a b, so by its own definition, it turns it into n. And honestly, these two properties are what confirm that exponential functions and logarithmic functions are inverses. Remember how you showed that two functions are inverses besides checking domains and ranges? If you do g of f of x, you get back x. If you do f of g of x, you get back x. In other words, when you put one inside of the other, they cancel. Here I'm putting the exponential function inside the logarithm. They cancel and give me back the exponent. Here I'm putting the logarithmic function inside the exponential function and they cancel again. So these two properties actually verify that logarithms and exponents are inverse functions. 5. Log base b of 1 over b to the n. We had an example like that in the previous video. It was log base 2 of 1 over 16. But once we figured out that 16 was 2 to the 4th power, then we could just rely on an exponent rule. The question this logarithm is asking is what power turns b into 1 over b to the n? Well, a negative power creates a reciprocal. Specifically, b to the negative n power is the reciprocal of b to the positive n power. So if you're forming a logarithm, and the argument is the reciprocal of something, there's a very good chance you're looking for a negative power. Well, what about this last one? It's a mess, but it's a good one to have in your arsenal of properties. Log base b of the nth root of b to the n power. Well, we had an exponent rule that says when you have a fraction power, you get a radical like this. So the answer to the question, what power turns b into this, the power really is the numerator, and the index is the denominator. That's the tricky one to remember, especially if you're just trying to commit letters to memory without understanding the rule that says anything to a fraction power, the denominator is the index of a radical and the numerator is actually a power. But it's this rule, as an exponent rule, that directly verifies that the answer to this log problem is n over m. So for example, if we had log base 13 of the 7th root of 13 to the 4th power, I would not have to figure out a thing because of the structure of the problem. The power that turns 13 into this, the power is the numerator and the index is the denominator. So it's not difficult to do if you really remember that exponent rule. These are not the only properties of logarithms, but these are some that naturally emerged from the problems that we did in the previous video and can be applied to some of the problems in the homework. In the next series of videos, we're not there yet, we will see 4 more properties of logarithms that will be pretty useful.